Great, thank you. First of all, let me thank Rafael and his team for having the courage to organize this conference. It's been great to finally be in presence and discuss with people, and it's been really fun. So I'm going to talk about this quantum time and quantum time measurements. The main part of the talk is work in collaboration with the previous speaker, Chris Saha. So what am I going to talk about? So I'm going to talk about time in quantum mechanics, and I'm going to show you a consistent formalization based on conditional probability amplitudes, but the main result I'm going to talk about is how you can consistently define a time observable in quantum mechanics. So time in quantum mechanics is basically a parameter that appears in the Schrödinger equation. If you take the formal structure of the theory, this is an axiom, the Schrödinger equation, and this is where time appears. And its meaning is that it indicates what is shown on a clock, which is on the wall of your lab. So you have your optical table where you're doing the experiment, and the clock is something like a classical system, which is on the wall of your lab. But of course, if you want to have a consistent formalization of quantum mechanics, you don't want classical systems in your axioms because that's inconsistent. You want something where everything is quantum, and classical mechanics should just emerge from quantum mechanics. So the idea we are exploring is, okay, just use a quantum clock, very simple. Use a quantum system as a clock, like a particle on a line or some other stuff. And then time is just entanglement, correlations between the clock system and your system where you're performing the experiment. This kind of mechanism has been discovered many times in the literature. And the basic idea is that you introduce a time Hilbert space in addition to your system Hilbert space. And then you introduce a constraint operator, which is just the sum of the clock momentum, which is equal to its energy. That's how you get back the Schrödinger equation, and the system Hamiltonian. And then you just say that the physical states are the ones that satisfy this constraint equation, J psi equals 0. And if you look at this, this is a kind of a Wheeler-DeWitt equation thing. And why are we doing all this construction? Well, if you look at this constraint, we are just saying that for physical states, the physical states are the ones where the Hamiltonian of the system is the generator of time translation invariants, time translations of the clock. That is the clock momentum. That's all it's saying. Okay, and well, it's a slight extension to quantum mechanics in which we are using a quantum property as a clock. So it's important to show how quantum mechanics can be obtained from this extension. I don't have time to go through this, but it's very simple to show that if you project the clock at time t, you get back the Schrödinger equation. If you project the clock to energy omega, you get back the time-independent Schrödinger equation. So it's very simple to see how conventional quantum mechanics arises from this construction. And basically, the main idea, just not to go through the formulas, is you have this psi double ket, which the double ket reminds you that you are, it's a state defined both on the system Hilbert space and on the clock Hilbert space. X, Y are the degrees of freedom of the system. T is the degree of freedom of the clock. If you project on the clock having time t0, then you get the state of the system at time t0. Okay, so everything works. Now, as I said, these ideas were introduced many times in the literature, but they were abandoned at the early, in the 80s because some objections were raised against these ideas. The most famous one is the Pauli objection. You cannot introduce a time operator because blah, blah, blah. And what we did is we removed these objections. I don't have time today to talk about this. And we also perfected the model. What I want to talk about instead is the time of arrival of a particle at a position. This is the work I've done with Chris. So the question is very simple. At what time does a particle arrive at a point in space where we put a detector? So particle is also a wave. We put a detector in some position. At what time does the particle arrive there? Very simple question. And when you tell experimentalists that we don't have a way to describe this kind of situation in quantum mechanics, because time is not an observable in quantum mechanics, it's just a parameter. So you cannot give a prediction of what quantum mechanics tells you about time measurements. Experimentalists are always surprised. They say, wow, we don't do these kinds of measurements all the time. Yeah, right. So indeed, we want to know how to get this. And the first idea is to formalize this is to realize that when we do these kinds of experiments, we do not measure the particle to get the time of arrival. What we are doing is measuring the clock, of course. Of course, we need to go to look also at the particle, but the time information, we do not get it from the particle. So it's hopeless to get a time of arrival operator if we only look at the observables of the particle. Okay, this is the main idea. So the time of arrival is a property of the clock. So it's an observable of the clock Hilbert space, not only of the particle. Okay, and okay, I don't have time to go through the formalization, but it's not very difficult to see. You start from the physical states. If you write them out explicitly, like the eigenstates of this constraint operator, they are entangled states of the clock and the state of the system at time t. This capital T is just a regularization parameter. You have to take the limit for this capital T to go to infinity if you want to get back the Schrödinger equation. But usually it just drops away at the final, when you calculate probabilities, so you don't have to worry about that. And then you introduce a projective Povm where you project the clock at time t. So this is the eigenstate of the clock showing that the time is t, and you project the particle at the position d of the detector. Okay, and you can create a projector. A projective Povm starting from that. Once you have a projective Povm, you can define an observable. And the most important thing, I won't go through the details, but the most important thing to notice is, as I was promising, this is a joint observable both for the clock and for the particle. Okay, and this is in contrast to many other time of arrival proposals that have appeared in the literature. Many such proposals exist. And typically, I mean, all of them basically consider the time of arrival as a particle, as a property of the particle. So as an observable in the system Hilbert space, not a joint observable like we do. And I think that's hopeless. Okay, once you have this projective Povm, you can calculate probabilities using the usual formalization of quantum mechanics. So the Born rule, you take the state, you use the projector, and you calculate the probability. But it's important to realize that this is a joint probability. It's the joint probability of the clock showing time t and of the particle being at position x. But if you want to know the probability of the time of arrival of the particle, you want just the probability of the clock showing time t. So you want a condition probability, the probability that the clock shows time t given that the particle has arrived. Once you have the joint probability, it's trivial to get the conditional probability using the Bayes rule. And if you go through the math, you find that it's basically a suitably normalized, it's the wave function, square modulus of the wave function suitably normalized. Okay, this gives you, according to our theory, the time of arrival probability distribution. Okay, and as you see, we are using basically a slight extension of quantum mechanics in which we are treating the time degree of freedom as a quantum degree of freedom, and then we are using the usual, the conventional quantum mechanics like the Born rule and so on and so forth. Observables, Born rule, and things of that type. So in summary, the idea, just to summarize the idea which is behind this, you take the projector for the particle being at the position of the detector and for the clock system to show time t. This gives you the joint observable, which gives you the joint probability. And then you get the clock probability just using the Bayes rule by condition. Okay? This is the idea. And one thing that's very nice of this proposal is that this is not limited to the time of arrival of a particle at a position, which is the prototypical problem that people analyze. But it's very easy to extend the same identical construction to measure the generic time at the time at which a generic event happens. Okay, so we want to know the quantum prediction of at what time did some event E happen. Okay, what do I mean by event? This is a tricky question. It's worth a whole talk just to define what I mean by event. In quantum mechanics, that's non-trivial. But for now, just let me say it's something that happens to a system. It means that the system acquires some value of some property, okay? So we just use the same trick that we did before. We have a joint projector on the time, which tells you at what time the system acquires the property, and on the system, we just use the projector that projects on the value that refers to the event E. For example, at what time you have a spin which is precessing in a magnetic field, you want to know at what time is the spin up, then all you have to do is use the projector for the spin up. Okay, that's the idea. And the construction that I've shown you up to now just trivially extends also to arbitrary situations of this type. So the advantages, as I said, there were many previous proposals of this. There are very many. It would take more than an hour just to do justice to them. Some of them are very nice, but our proposal indeed can describe situations that other proposals cannot, like, for example, the case in which the particle goes through the detector position multiple times, even a case which you say, why would you think about that? The situation in which the particle is fixed at the detector position. So why is it important for a time of arrival to describe that situation? Well, because we are doing quantum mechanics. So a wave function that describes a particle will always have, unless you are considering a bounded wave function, will always have a component, a tail of the distribution in which the particle is at the detector position since the very start and that's a probability amplitude that the particle is already at the detector position. So you cannot really ignore this like some people do. And then as I've shown, you can extend it to arbitrary event. And well, okay, there's also the possibility of describing multiple clocks. But the most interesting part is that there are testable differences with respect to other proposals. This is some preliminary calculations we did, and we showed that if the particle is in a superposition of traveling towards a detector from two different sides, then what happens is that you have interference fringes in time, which is what you would expect. Of course, we are doing quantum mechanics. We expect to have interference fringes, but not all of the other proposals do predict interference fringes in this situation. So maybe it would be interesting to do an experiment. Okay, conclusions. Maybe I went too fast. I've shown you how you can extend quantum mechanics in order to describe time as a quantum degree of freedom, not to rely in the axiomatic structure of the theory on some abstraction like classical clocks. It's not too difficult. Then I've shown you how you can recover the textbook quantum mechanics just by conditioning on the clock, and you reobtain the Schrödinger equation and the state of the system at some time. And then I've shown how this construction can be used to describe time of arrival measurements or generic measurements of time of when some event happens. And take-home message is a quantization of time and time of arrival based on conditional probability amplitudes. The quantum time paper is this one, and the paper with Chris is here. Thank you for your attention.
Thank you very much. And the question session is open. Lots of questions, I think. First.
Hello, thanks for the nice talk. I was wondering, it's probably an obvious question, but this was non-relativistic, and is it possible to somehow extend this theory to include special relativity or to go even further? Because time usually is an external parameter that you sort of put on your system, and now here it seems to be part of the system.
Excellent question. We have the relativistic extension of this, but I'm not ready to talk about it. It's really, let me tell you something, it's really difficult, because I've been working on this for many years.
Thank you. Are there any questions from the online audience? You don't see it?
No, I don't think
so. Fourth.
Excuse me if I may. Sorry, is it possible to account for the uncertainty of measurement in time? I mean, the jitter, using this model?
Sorry, say again?
Is it possible to account for the uncertainty? Is it possible to account for the uncertainty of measurement in time? I mean, the jitter, using this model?
That's a great question. So, yes, if you want to know the uncertainty in a time measurement, given that you assign some energy to your clock, of course you need, for the ideal clocks I've used here are idealization that need infinite energy and infinite energy spread. But if you have finite energy and finite energy spread, then you will have some uncertainty in your time measurement. And this is just given by the usual by the usual Heisenberg-Robertson uncertainty relation applied to the clock system, okay? So you can certainly do that. But if, and this is a paper that appeared in the archive last week that I did in collaboration with Matteo Fadel from ETH Zurich. A more interesting question is, can you give a time-energy uncertainty relation when you want to measure the time at which an event happens, okay? So not something restricted to the clock, but something that refers to an event, okay? And the answer is yes, you can do that. You have to consider these conditioned observables I was talking about today, and you can give a time-energy uncertainty relation.
Okay, still no online questions? No.
No.
Okay, I think it's your turn.
Thanks for the talk, Lorenzo. I have a question on the first part where you introduced this time, this clock. And I find it a bit surprising that, so assuming you have to keep time for the whole system you're observing, or let's say for the whole universe, this clock has to be entangled with the rest of the universe to do this, in order to do this. So you need an infinite amount of degrees of freedom for the clock. How?
No, it's entangled only on the time degree of freedom. It's the entanglement is just on the time degree of freedom, okay?
But it has to be entangled with everything else.
No, just with everything that evolves. if you have subsystems that do not evolve, the entanglement goes away, okay? Which is what you would expect. If nothing evolves, the clock is not tracking its evolution just because it's static.
Yeah.
No. Eigenstates of a Hamiltonian do not evolve. So those get factored out. All the rest is entangled, sure.
Yeah.
I just wanted to say that even the eigenstate has the phase.
Oh yeah, but that's not observed.
And that is time dependent.
The phase of the eigenstates of the energy are not observable, and they factor out. So.
But if you have two subsystems, then this phase
Yes, in this
could be of
case,
relevance.
yes. If you have a superposition, then yes, you would have. Yes. Sorry, Perola, maybe it was.
No, it's okay because I have more or less the same kind of question, but
Well, your turn.
Sorry. Well, but I find this. I didn't understand your answer to the question yet because it gives the impression that it is more or less. I think that what they mean is that there is as if you consider a quantum measurement apparatus, and then you should consider that it's coupled to an environment that evolves with respect to this quantum T ancillary to T that you put, or not?
Oh no, there's no. Maybe I'm not understanding your question, but there's no interaction between the system and the clock. Okay.
Yeah.
It's just the sum of the free Hamiltonian of the system and the free Hamiltonian of the clock. The correlations just come out because of the Wheeler-DeWitt equation. The constraint equation is what puts in these correlations, this entanglement.
Okay, this is understood. But maybe we can discuss this point later. But my real question was: can you generalize your kind of description to any measurement? In what sense time is different in this sense?
Oh no, just if you take textbook quantum mechanics, time measurements cannot be described because there's no time operator.
Okay.
That's what we have been doing. So with this construction, you can introduce a time operator. These are its eigenstates. The eigenvalues is just the T. And then you can describe time measurements as any other observable.
As any other measurements, yes.
Yeah, exactly. And then you have the measurement. And for example, the way, just to give an idea of everybody would say, okay, time observables, they cannot be defined in quantum mechanics because of the Pauli objection. Pauli was saying that if you have a time observable where the commutator between time and energy is equal to IH bar, then the Hamiltonian must have infinite unbounded spectrum from above and from below. But notice that in this case, we have that the time observable acts in a different Hilbert space from the Hamiltonian of the system. So it's true that the Hamiltonian of the clock has unbounded spectrum. That's an idealization. If you want perfect clocks, you need that. But the important thing here, which resolves Pauli objection, is that the Hamiltonian of the system can be anything. It can have any spectrum. And it certainly commutes with time because it acts on a different Hilbert space. So it certainly commutes with time. Okay? Just to give you an example of why we are doing the construction in this way.
Yeah, okay.
We have an online question, so maybe we are already into lunchtime, but maybe we can take one online question, one final online question. I think you have been unmuted, so please.
Yeah, thank you for the talk. I just wanted to know how you describe the revival phenomena with your model. Is it possible? Is it easy, or you need some extra information?
Yeah, here I've given you can do this kind of construction also for mixed states. So you can describe irreversible phenomena, but the basic idea is that you need to purify and then consider only pure states. So this revival is just a unitary evolution, and then there's nothing special in this kind of situation. Okay, so it's just one specific instance of time evolution in which the degrees of freedom get entangled with some external degree of the wave packet. Just the wave packet dies away, and then its degrees of freedom are transferred to another ancillary system, and then they're transferred back, and you have a revival. So if you consider in this psi, you consider both the degree of freedom of the wave packet and of the ancillary system, it's just a unitary evolution. So there's no big deal.
Thank you.
Thank you very much. I think we can have more discussion during the break. So let's thank Lorenzo and all the previous speakers in this session.